Yes, Unit 5 Coordination Compounds. In this chapter, the objectives are: after studying this unit, you will be able to appreciate the postulates of Werner's theory of coordination compounds, know the meaning of the terms coordination entity, central atom, ion, ligand, coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic and heteroleptic. Learn the rules of nomenclature of coordination compounds. Write the formulas and names of mononuclear coordination compounds. Define different types of isomerism in coordination compounds. Understand the nature of bonding in coordination compounds in terms of valence bond and crystal field theories. Appreciate the importance and applications of coordination compounds in our daily life. Coordination compounds are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. In previous unit, we have learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electron. Let's read again. Transition metals form a large number of complex compound in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electron. In the modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological system. Let's read that again. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of the biological system. Chlorophyll, seen in plants, hemoglobin, seen in the red blood cell, and vitamin B12 are coordination compounds of magnesium. Iron, chlorophyll is a coordination compound of magnesium. Chlorophyll is a coordination compound of magnesium. Hemoglobin is a coordination compound of iron, and vitamin B12 is a coordination compound of cobalt. Chlorophyll, coordination compound of magnesium, hemoglobin, of iron, and B12 vitamin, of cobalt. Hemoglobin, we see that there are four active sites which are of iron, which can bind with oxygen or carbon dioxide to form or to transport them. If it binds with oxygen, it is called oxyhemoglobin. If it binds with carbon dioxide, it is carbaminohemoglobin. Chlorophyll is a coordination compound of magnesium. Hemoglobin is a coordination compound of iron. Vitamin B12 is a coordination compound of cobalt. Let's continue reading. Variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing, and medical chemistry. Variety of metallurgical processes, let's read this again. Uses of coordination compounds, applications. Variety of metallurgical processes, act as industrial catalysts, analytical reagents involve the use of coordination compounds. They also find many uses in electroplating, textile dyeing, and medical chemistry. That gave a total of 6 uses of applications of coordination compounds. 1. Help in metallurgical process, act as industrial catalysts, and analytical reagents. You involve the use of coordination compounds, help in electroplating, textile dyeing, and medical chemistry. Metallurgical processes, industrial catalyst, analytical reagents involve the use of coordination compounds. Fourth use, used / help in electroplating, medical chemistry, textile dyeing or textile industry. The first use, metallurgical processes act as industrial catalysts used with analytical reagents, used or help in electroplating, help in medical chemistry, help in textile industry. These are the uses mentioned in NCERT. The next topic, the first topic, Werner's theory of coordination compounds. Alfred Werner, 1866 to 1919, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of primary valence and a secondary valence for a metal ion. Binary compounds such as chromium chloride or chromium trichloride, cobalt chloride, palladium chloride have primary valence of 3, 2, and 2 respectively. In a series of compounds of cobalt 3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl or silver chloride on adding excess silver nitrate solution in cold, but some remained in the solution. Let's read again. It was found that some of the chloride ions could be precipitated as silver chloride on adding excess silver nitrate solution in cold temperature. When we take cobalt 3 chloride or COCl3 with ammonia, it was seen that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate, but some remained in the solution. They are basically describing a reaction here. The reaction is basically if you take COCl3 plus AgNO3, this will normally there will be a normal displacement reaction where AgCl is precipitated and these both will react. But it was seen that if these both, in case if we take along with ammonia, with series with ammonia with NH3, this compound plus ammonia if we take, even if we add excess amount of AgNO3 or silver nitrate, stoichiometrically we found out that although most of the Cl ions here from here would be displaced and precipitate out as silver chloride, some of the chloride ions were still found to be in the solution without precipitating out. They are basically describing a property of complexes or coordination compounds. Coordination compounds salt complexes do not dissociate in a solution. Another way of saying this is they do not lose their identity. Normally, this is the definition. Normally, if we add NaCl to water, the NaCl will dissociate into Na plus and Cl minus, but in case of in this dissociation, NaCl dissociates, but complex compounds or coordinate compounds do not dissociate in water or any other substance. That is why when we saw the displacement reaction of when we took COCl3, normally if we did not take NH3, it would have been completely displaced with CONO3, I believe. I don't know the reaction. AgCl would have been completely liberated or completely precipitated. But because we took NH3, these both, the COCl3 and NH3, are basically forming a complex or a coordination compound, which will retain its identity. As such, this Cl3 will not be, all the Cl3 molecules stoichiometrically will not be equal to the AgCl precipitated. Let's read again. Alfred Werner, 1866 to 1919, a Swiss chemist, was the first to formulate his ideas about structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concepts of a primary valence and a secondary valence for a metal ion. Binary compounds such as chromium chloride, cobalt chloride, palladium chloride have primary valence of 3, 2, 2 respectively. In a series of compounds of cobalt 3 chloride or cobalt trichloride with ammonia NH3, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate in cold solution, but some remained in the solution. When we take 1 mole of cobalt chloride and NH3, 6NH3, it gave 3 mole of AgCl, which was yellow color solution. Here we see that the chlorine amount is tallied. Here we have 3 chloride, 3 Cl. Here also we got 3 mole of Cl. Let's see the second case. 1 mole of COCl3 and 5 NH3. This is a purple color solution. In this case, we see that only 2 moles of AgCl was precipitated. Here, we took 1 mole of COCl3, which will have 3 chlorine. Here, we only got 2 mole of AgCl, which only refers to 2 Cl. The 1 Cl will remain as a coordinate compound inside the solution. And the third case, COCl3 with 4NH3, which is a green color solution, gave only 1 mole of AgCl. The main solution had 3Cl, but we got only 1Cl. In the fourth case, we took 4NH3, but this is an isomeric, like it's an isomeric coordination compound. Even though the empirical formula is same, the color is different because it's an isomer. It gave 1 mole of AgCl. Here as well, it had 3 chlorine but only gave 1 chlorine when the reaction took place. These observations, together with the result of conductivity measurements in the solution, can be explained if 6 groups in all, either chloride ions or ammonia molecules or both, remain bonded to the cobalt ion during the reaction, and 2, the compounds are formulated as shown in 5.1 table, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valences are 6. Let's read that again. As we saw here, the cobalt chloride, based on the amount of NH3 we took, just giving less and less of AgCl and retaining the chlorine ions. The first case this should happen is 6 groups in all, either chloride ions or ammonia ions or both, remain bonded to cobalt ion during the reaction. If 6 molecules of either chloride ions or NH3 molecules remain bonded to CO, then only it is possible. The second scenario, the compounds are formulated where the atoms within the square brackets form a single entity which do not dissociate under the reaction conditions. Otherwise, whatever they are showing here, if these do not dissociate, then also it is possible. Then also what we saw here, where it was giving less and less amount of AgCl, when these don't dissociate, then also it is possible that we get them. This is the second case. And Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. Each of these examples, the secondary valences are 6. In this case, they are saying the first example is CONH3 6 Cl 3 minus 3 plus. This is one of the example of a coordination compound where whatever is inside this bracket does not lose its identity. When dissociation, it will form CONH3. Oops. It will form CONH3 6 times with a charge of 3 plus Cl 3 minus ion. 3 that was a mistake. 3 Cl minus ions. In the first case, when we saw here, where we took 1 mole of CoCl2 plus 6 NH3, we got 3 moles of AgCl, where the number we took of the Cl tallied here. That is the case I showed here, where this is the compound when we take 6 unit amount of NH3, the Cl minus will be outside and it will dissociate. And the second kind of compound is CoCl, where we saw the CoCl3 dot 5NH3. This color, if you remember, was purple color. Whereas this molecule is yellow colored. Yes, yellow. This molecule is yellow color, or the solution is yellow colored. This one is purple color. Purple color solution, where we take 5NH3, we will get CoCl NH3 5, where 1 Cl will be less, and here the charge will be it will dissociate into CoCl NH3 5 whole charge of 2 plus and 2 Cl minus ions. In the second case, where we took 1 mole of CoCl3 plus 5 in 5NH3 in series, we only got 2 AgCl. We lost 1 chlorine. This is the reason we lost this 1 chlorine, because it was inside the complex. This metal atom, which is taking the bond from these are called ligands, whereas this is called the cobalt atom, or the transition metal atom. It is called central metal ion, CMI, which will accept the electron. If it is outside, it can dissociate, but if it's inside, it will take all the electrons. Basically, what our ligands are, for example, this compound CONH3 6 times Cl 3 minus and 3 plus. Basically, how this ligand is formed is, this is the CO atom. This is a transition metal which comes under the 3D series, and all the NH3 molecules, 6 NH3 molecules, and NH3 molecules having a lone pair of electrons. If you remember the nitrogen's valency, it has 5 valence electrons and it has one lone pair of electron. Each of this nitrogen will have lone pair of electron. When these NH3 atoms have lone pair of electron, they will send it to cobalt as a coordinate bond. All coordinate compounds, these are coordinate bonds, meaning there is no sharing, it is the sharing of electrons where one atom is completely donating both the electrons. Coordination bonds. That is why where these NH3 molecules, all of them are called like ligands, and the cobalt atom which is accepting all the electrons or all the ligands is called central metal ion. These 3D series or transition metals can accept all these electrons because they have empty d orbitals, empty d orbitals. And because these ligands are forming coordination bonds, we call them coordination compounds. And here in this case, cobalt is taking electrons from 6 ammonium or NH3 molecules, and this complex will act as a single ion having a whole charge of 3 plus. Chlorine will get dissociated in this case when it's outside. The second case, where we only had 5 molecules of ammonia, COCl NH3 5 times, only 2 Cl were outside, so the charge became 2 plus, and the AgCl precipitated reduced from 3 to 2. Here as well, if you see in this case, the number of atoms, molecules surrounding cobalt is 6. Here as well, including Cl, 1 plus 5, the total number surrounding the central metal ion is 6. And in one more case, where we took COCl3, 4NH3, in this case the solution was green in color. In this case, the COCl3, 4NH3, it formed a complex of COCl2, NH3 4 times. This was inside with a charge of 1 plus and Cl minus. With this, the total AgCl precipitated reduced from 3 to 1 mole. Even there is one more case where the solution with the same empirical formula is violet in color. Here as well, it is an isomerism. Even though both have the similar empirical formula, they have different structures. But they will also liberate only 1 mole of AgCl, or be displaced to give 1 mole of AgCl. How they found out if 3Cl is released? Here we saw that here we see that they said this much 1 mole of COCl3 6NH3 gave 3 mole of AgCl, or this solution of 1 mole gave 2 mole of AgCl. How they found this out is via the conductivity. Solution conductivity, if it is 1:3 electrolyte, that means it gave 3 chloride ions. It will be of charge 3 plus and 3 times of 1 minus. Here in the first case scenario, where all the 3 chloride ions were substituted, and in the second case, in this case, it will be 2 plus and 2 1 minus. It will be 1:2 electrolyte. Only 1 2 plus cation will be there, but 2 1 minus anions will be there. But in this case, it is 1:1 because 1 1 plus anion and 1 1 minus cation. Anion. The anion, cation will be the complex, whereas the anion will be the 1 chloride ion liberated or precipitated. Color of the first solution, where 6V2NH3 is yellow, 5 is purple, 4 is green or violet. Note that the last two compounds in the table have identical empirical formula, COCl3 4NH3, but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are: in coordination compound, wait a second. Yes, the main concept here was Werner said that metal, the CMI, the central metal ion, has two kinds of valencies. One, primary valency, where in case of COCl3, here the primary valency of cobalt is 3 because it is bonding to 3 chloride ions. This is the most basic common. And the secondary valency, this secondary valency is equal to the number of ligands the CMI, central metal ion, is bonded to. Here, in case of CONH3 6 times, here the central metal ion is bounded to 6 NH3, so its secondary valency is 6. The number of groups, secondary valency is the number of groups bound directly to the metal ion. In each of these examples, secondary valences are 6 because here 1 chlorine is there, 5 NH3 is there, 1 plus 5, 6. Here 2 chlorine is there, 4 NH3 is there, 4 ammonia, 4 plus 2, 6. So the secondary valency of all these 4 compounds or complexes, coordination compounds, is 6. So let's come back to the postulates again. The main postulates about Werner. In coordination compounds, metals show 2 types of linkages, valences, primary and secondary. The primary valences are normally ionizable and are satisfied by negative ions. The secondary valences are not ionizable, they are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. The ions groups bound by the secondary linkages to the metal have characteristic spatial arrangement corresponding to different coordination numbers. The primary valence is ionizable and is satisfied by negative ions. Secondary valence is non-ionizable and is satisfied by negative or neutral ligands. The secondary valence is equal to the coordination number of a metal. This coordination number is fixed. These are the postulates, and one more postulate. And the arrangement of this is what we call polyhedra. Yes, polyhedra. When these cobalt takes NH3 of 6 NH3 atoms, how this will be arranged in space? Objective is to arrange them spatially in such a way that minimum repulsion, maximum stability. We saw that geometry, and we saw that in chemical compounds first PU we saw various geometry and shape of various compounds which are arranged in that way to gain minimum repulsion and maximum stability. With the same goals, even the complex compounds arrange in special structures. This arrangement we call it as polyhedra. In modern formulations, such spatial arrangements are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. In the same CONH3 case, CONH3 6 times. In case if this will be, if it was instead of let's take an easier example. This is the case. The metal atom, this is 4. The color may be either violet or green. This cobalt ion transition element is a CMI, central metal ion. These both are different ligands. This outer atom here, in case it is a chloride ion, it can either be metals or non-metals. Here it is a chloride non-metal, which is what we call counter ions. And the arrangement, spatial arrangement, of the complex is called coordination polyhedra. Werner further postulated that octahedral, tetrahedral, and square planar geometrical shapes are more common in coordination compounds of transition metals. Thus, CONH3 6, CONH3 5, and COCl2NH3 4 are octahedral structures, while NiCO3 and PtCl4 are tetrahedral and square planar respectively. In the COCl3 case, in the all the coordination compounds from these ones, all these 4 are octahedral. All these are octahedral in structure because there are 6 ligands. But in case of this octahedral is similar to the octahedral structures we saw in chemical bonding. But in case of nickel cobalt 4, nickel carbon and carbon monoxide times 4, and platinum chloride 4, as these are similar to how these are tetrahedral. Example for tetrahedral in chemical bonding is CH4, where one carbon is bonding with 4 hydrogens. The structure will be where this is the thick bond, and this is the thin bond. The angle being 109 degrees, 109.28 something degrees, 26 I believe, I'm not sure. The same way this will also be along with platinum. Arranged in a tetrahedral manner. Here's an example question. On the basis of the following observation made with aqueous solution, assign the secondary valences to metals in the following compounds. Formula: moles of AgCl precipitated per mole of the compounds with excess AgNO3. PdCl2 4NH3 2. Here we see that it has has 2Cl. It also precipitated 2Cl. So we can understand from this that this compound, in the complex, there is no Cl in the complex. So the secondary valence for PD should solely come from 4NH3. In that case, it should be, the secondary valence should be 4 for PdCl2 in series of 4NH3. In the second case, of NiCl2 and 6H2O, even water can act as ligand, a neutral ligand. Here we see that 2 Cl molecules are there, and we got 2 AgCl, which is equal to the number of Cl here and here, so it is equal. As such, we can understand that there are no Cl in the complex, and it should be based on nickel's secondary valence. It should be 4. No, it should be 6, because there are 6 H2O molecules. In a third case, where we have 4 Cl molecules, but got no AgCl, which means that all 4 Cl molecules are in the complex and not as counterions, which means here the valence of the platinum should be 4. First, this one here, we saw that it was also 4 here as well. Here in the fourth case, where COCl3 and 4NH3, we see that we got 1 chlorine, where there are 3 chlorines here. We only got 1 chlorine. As such, we can determine that 2 chlorine are inside the complex, and 4NH3, since COCl coordination number is 6, it will be secondary valence will also be 6. Platinum Cl2, in the second case scenario, where we have 2Cl in the formula but we got 0Cl, we have two NH3 molecules. Since platinum's coordination number can be assumed to be 4, we can assume that there are 2 Cl in the molecule in the complex along with 2 NH3. Here as well, the secondary valence is 4. We can correct it. The first one being 4, correct. Second one being 6, correct. Third one being 4. Third one is platinum. It seems that platinum has also bonded with these two HCl molecules. As such, here as well we can take it as 6. Even HCl acting as a ligand. And in the fourth case it is 6, correct. Fifth case it is 4, correct. Difference between a double salt and a complex. Both double salts as well as complexes are formed by the combinations of two or more stable compounds in a stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl MgCl2 6H2O, more salt, potash alum, etc. dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 ferrate cyanide of potassium ferrate cyanide do not dissociate into ferrous and cyanide ions. What we should remember here is the importance in that paragraph. First, names and formulas of the double salt. The second importance in that paragraph is the difference between double salt and coordination compound, which is nothing but double salt, if you add in water, dissociate. Coordination compound, dissociates. No, it doesn't dissociate. This is the difference they gave between coordination compound and double salt. And the names of examples for double salt: being 3 examples, which is carnallite, Second one, more salt. NH4 twice. And 6H2. The third one, potash alum with potassium and aluminium along with sulfate and 12 water molecules. Yes, these are the salts which you can get in match the followings, etc. Carnallite being KCl, MgCl2 and 6H2O. Mohr salt FeSO4, NH4 twice, NH4 is NH4, NH4 twice, SO4 and 6H2O, and potash alum being KAl, potassium and aluminium disulfate with 12 molecules of water. Let's continue. The main difference between double salts and coordination compounds is that coordination compounds do not dissociate into ions. We can indeed spend some time to read about Werner 1866 to 1919. Werner was born on December 12, 1866 in Mulhouse, a small community in the French province of Alsace. His study of chemistry began in Karlsruhe, Germany, and continued in Zurich, Switzerland, where in his doctoral thesis in 1890 he explained the difference in properties of certain nitrogen-containing organic substances on basis of isomerism. He extended Van 't Hoff theory of tetrahedral carbon atom and modified it for hydrogen. Werner showed optical and electrical differences between complex compounds based on physical measurements. In fact, Werner was the first to discover optical activity in certain coordination compounds. He, at age of 29 years, became a full professor at Technische Hochschule in Zurich in 1895. Alfred Werner was a chemist and an educationist. His accomplishment included development of the theory of coordination, how atoms and molecules are linked together, was formulated in a span of only 3 years from 1890 to 1893. The remainder of his career was spent gathering the experimental support required to validate his new ideas. Werner became the first Swiss chemist to win the Nobel Prize in 1913 for his work on the linkage of atoms and coordination theory. The next topic, definitions of some important terms pertaining to coordination compounds. The first term being coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, COCl3NH3 is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO3, NiCO4, platinum chloride, and NH3 twice, FeCN6, ferrite cyanide, and cobalt NH3 6 times. Central atom or ion in a coordination entity, basically whatever a coordination entity is, whatever is in these square brackets in coordination compounds is what we call a coordination entity. Whatever is in the square brackets, we call it coordination entity. Here we see this one, all of these are coordination entities. The second part is coordination atom or central metal atom. In a coordination entity, the atom ion to which a fixed number of ions groups are bound in a definite geometrical arrangement around it is called the central atom or ion. For example, the central atom in the coordination entities are nickel 2 plus, cobalt 3 plus, and ferric ions respectively. These central ions are referred to as Lewis acids. Lewis acids accept electron, and Lewis bases give electrons, donate electrons. Ligands, the third one. The ions or molecules bound to the central atom in the coordination entity are called ligands. These may be simple ions such as chloride, small molecules such as water or NH3, larger molecules such as H2NCH2, CH2NH2, or N, this one, or even macromolecules such as proteins. When a ligand is bound to a metal ion to a single donor atom, as which Cl minus, H2O, or NH3, the ligand is said to be unidentate. When a ligand can be bind through two donors atom, as in this molecule, ethane 1,2 diamine or oxalate, here we see that normally in NH3, N having lone pair will form a coordinate bond, and in one molecule only one ammonia molecule or N molecule or N atom will form a coordinate bond, and basically this is called unidentate. But in this case, in the ethane 1,2 diamine, this N will have lone pair, this N will also have lone pair. These will form, in this single molecule, will form two coordinate bonds with the metal. This is called a bidentate or didentate. And in case of oxalate ion as well, oxalate of C2O42 minus of these can also form two bonds with these lone pair of electron. As such, this can be called as bidentate or didentate. This property of denticity is the number of bonds formed or capable of forming, no, it is formed itself. Number of bonds formed by a single ligand with the metal ion. This is the property of denticity. In case of oxalate, we see it is bidentate, capable of forming two coordinate bonds. In case of ethane 1,2 diamine, I believe even this can form bonds with, this is not bidentate but hexadentate. This molecule, which is the EDTA molecule, which is hexadentate. A single molecule can form a total of 6 bonds. In case of this molecule, ethane 1,2 diamine, ethane 1,2 diamine here. These lone pairs can form two bonds. This one ligand can form two bonds, so it is didentate or bidentate. That is case with ethane 1,2 diamine or oxalate. The ligand is said to be didentate, and when several donor atoms are present in a single ligand, as in NCH2 CH2 NH2, here the ligand is said to be polydentate. Ethylene diamine tetraacetate, the EDTA, this one is an important hexadentate ligand, because here as well they have the lone pair. This four lone pairs from oxygen and 2 lone pairs from the 2 nitrogen atoms. That's why it has a 6 denticity. So we call it as a hexadentate ligand. It can bind through nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. When, let's see it again, when a di or polydentate ligand uses its atoms simultaneously to bind to a single metal ion, it is said to be a chelate ligand. When a polydentate ligand uses its atoms to form 2 or more bonds to a single metal ion, it is called a chelate ligand. Uses its 2 or more donor atoms simultaneously to bind to a single metal ion. It is said to be a chelate ligand. This is referring to the ligand. The number of such ligating groups are called denticity of ligand. Such complexes called chelate complexes tend to be more stable than similar complexes containing unidentate ligands. Ligand which has 2 different donor atoms and either of the 2 ligates in the complex is called ambidentate. Ligand which has 2 different donor atoms and either of the 2 ligates in the complex is called ambidentate. In case of nitro group, nitrogen can act as a ligand or this oxygen can act as a ligand. This is called ambidentic ligands. Ambidentate ligands where there are two or more donor atoms, which can be either here it is nitrogen, here it is oxygen, but only single of them is in the complex. It's like forming the bond with the metal. This is called ambidentate ligands. Here we call it nitro O because oxygen is forming the bond. Here we call it as nitro N. Ambidentate ligand like this, nitro O and nitro N. Or in case of thiocyanato, if in the SCN group, if sulfur is forming the bond, it is called thiocyanato S. If nitrogen is forming the bond, it is thiocyanato N. Examples of such ligands are NO2 minus and SCN minus. NO2 minus can coordinate either through nitrogen or oxygen to a central metal atom ion. Similarly, SCN can coordinate through sulfur or nitrogen atoms. Let's read again. When a di or polydentate ligand uses 2 or more atoms to bind to a metal ion, it is said to chelate ligand. The number of those. The number of such ligating groups is called density of the ligand. Basically, if I have to explain again, in a ligand, the number of donor groups, not atoms, which are part of the ligand, which can simultaneously form bonds with the metal atom, with a single metal atom, the single metal atom is the density of the ligand. In a ligand, the number of donor groups which can simultaneously form bonds with a single metal atom is the density of a ligand. This is a ligand. Let me repeat again. In a ligand, the number of donor groups which can simultaneously form bonds with a single metal atom is the density of that ligand. This is the definition of density. And ambidentate ligands, being in a ligand, there are two or more donating groups, but only one of the groups can actually form bonds. This is called ambidentate ligands. This we can see in case of NO2 and SCN, thiocyanato and nitro groups. And the fourth or D concept is coordination number. The coordination number for metal ion in a complex can be defined as a number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ion PtCl6 and NiNH3 4 times, the coordination number of Pt, platinum and nickel are 6 and 4. In platinum, a single platinum ion is bonded to 6 chloride ions, and in nickel 4 ammonia ions are bonded to a single nickel ion. So the coordination number in platinum, where 6 are bonded, is 6, and in nickel, where 4 ammonia ligands are bonded, it is 4. Similarly, in the complex ions FeC2O4 thrice, where C2O4 is the oxalate ion and has a density of 2, and COEN thrice, The coordination number of both Fe and CO is 6 because ethane 1, 2 diamine and oxalate ion are didentate ions. Let's read the definition of the coordination number again. The coordination number of a metal in a complex can be defined as the number of ligand donor atoms which the metal is directly bonded to. But here, in the normal case where the ligands are unidentate, in platinum and nickel examples, we see that it will be 6 and 4 respectively. But whereas in special cases where the ligands are bidentate, it will be equivalent to denticity, the coordination number. Coordination number is the number of ligands directly bonded to the metal atom. Cn can be calculated with denticity times denticity of ligand times number of ligands bonded to the CMI. If how we should take denticity values is unidentate value is 1, bidentate value is 2, tri is 3, and so on. This is how we find the coordination number, which is Cn. En is nothing but ethane 1, 2 diamine. The structure which I drawn before. The coordination number of both Fe and CO is 6 because oxalate and ethane diamine ligands are didentate or bidentate ligands. It is important to note here that coordination number of the central atom ion is determined by only the number of sigma bonds formed by the ligand with the central atom. It is important to note here that the coordination number of central atom ion is determined by only the number of sigma bonds formed by the ligand with central atom. Pi bonds, if formed between the ligand and the central atom, are not counted for this purpose. In case of this bond, in case of here, we consider only one bond here because one is a sigma bond and one is a pi bond. Let's continue. Coordination sphere. As for if you have confusion why we counted denticity, meaning here we took that denticity is 6 where only 3 bond where we only took 3 molecules, but the density we multiplied by 2. Why that is the reason? Because in case of oxalato ion, where these oxygen are bonding, even they form a single bond, coordinate bond with this lone pair, and even if we consider that these form a double bond, let's assume it is not correct, but let's assume in one kind of molecule these form a double bond, but still we consider them as 2 itself, because 2 oxygen molecules are binding here. As such, we only consider a single bond, but we still take 2 because 2 are binding here, and density definition is a number of different groups in a single ligand simultaneously bonding together. As such, even if they form pi bonds, we only consider a single bond for each and every donating group. The next is coordination sphere. The central atom, ion, and the ligands attached to it are enclosed in a square bracket and is collectively termed as the coordination entity or coordination sphere. The ionizable groups are written outside the bracket and are called counterions. For example, in the case of complex K4 FeCN6, the coordination sphere is FeCN6 4 minus, and the counterion is K plus. And next topic, coordination polyhedron. The spatial arrangement of ligand atoms which are directly attached to the central atom defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. Let's see it again. The spatial arrangement of ligand atoms which are directly attached to the central atom, ion, defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. For example, CONH36 3 plus is octahedral because there are 6 ligands attached here, whereas NiCO4 is tetrahedral and PtCl4 is square planar. The figure shows the shapes of different coordination polyhedra. Here the L signifies ligand, whereas M signifies metal atom, and the thick bonds, these ones signify that they're coming out of the screen, whereas the thin bonds, the lined bonds, represent that they are going inside the screen. A 3D structure where this forms an octahedra. And this is a tetrahedral structure, one thick bond, one thin bond, 2 plain bonds, and a square planar structure where in chemical bonding this happens because there are 2 lone pairs where the geometry may be octahedral, but due to the lone pair bond pair repulsion, they form a square planar structure. This is a trigonal bipyramidal. This is the square pyramidal because it forms a square base and a pyramid structure. it is very similar to chemical bonding and normal molecule shapes. Shapes of different coordination: polyhedra. M represents the central atom, ion, and L represent an unidentate ligand. L represent a unidentate ligand. The next is oxidation number of central atom. The oxidation number of central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parenthesis following the name of the coordination entity. For example, oxidation number of copper in CuCN4 3- is +1 and is written as Cu1. Here Cu CN4 whole power 3- the charge or oxidation, the ON of oxidation number of copper is this 3- charge is the total charge obtained by the complex, or basically the copper, after the sharing of the CN electrons. CN, how should we know if it's unidentate or bidentate? Is CN, we see that it is unidentate because carbon is the one forming a coordinate bond with the metal. It is unidentate, so we can count that the copper will gain 4 pairs of electrons. So when CN4 will have a -4 charge, collective -4 charge, copper will have a collective +4 charge. But this, with respect to the whole complex charge, which is due to the sharing of electron, you will know that the oxidation number of copper will be, copper ON will be equal to 4 plus of -3, which is 1 plus 1. So the ON of copper is +1. In case of CO, Cl2, NH3 4 times with a whole charge of -1, then the ON of CO will be, here there are 6 groups. Cl2 is a unidentate group, the Cl is a unidentate group, it's a unidentate group. NH3, where NH will donate the lone pair of electrons, is also unidentate. The charge is actually +1 because there will be Cl- outside. The charge will be +1, and so the total charge For the this side, the collective charge will be -6 and the cobalt charge will be +6. The total charge of cobalt actually we see that the charge is not +6. The charge contributed by NH3 is 0, as NH3 is a neutral ligand, where Cl is -1 each, so it will be -2 is the charge of this, or the total here, and +2 will be the charge of cobalt. Let's continue reading. The next topic, homoleptic and heteroleptic complexes. In homoleptic complexes, we see that only a single ligand is there. In case of CONH3 6 times, only NH3 is the ligand. In heteroleptic, there are more than one kind of ligand. In here, NH3 is there and Cl is also acting as a ligand. Complexes in which a metal is bound to only one kind of donor group are known as homoleptic ligands. Complexes in which a metal is bound to more than one kind of donor group or ligand are known as heteroleptic ligands. The next main topic, nomenclature of coordination compounds. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas, writing systematic names, particularly when dealing with isomers. The formulas and names adopted for coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry (IUPAC). Formulas of mononuclear coordination entities. It is under the nomenclature. The formula of a compound is shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination compounds are entities contain a single central metal ion. The following rules are applied while writing the formulas. When the CMI is 1 in number, which is mononuclear coordination compounds. Mononuclear coordination compounds. The central atom is listed first. The ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. It only depends on the alphabetical order. Polydentate ligand are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. The first point again, the central atom is listed first. The ligands are then listed in alphabetical order. The placement of a ligand in list does not depend on its charge. Polydentate ligands are also listed alphabetically. In case of abbreviated ligands, EDTA, the E is the first letter is in the abbreviation is used to determine the position of the ligand in the alphabetical order. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligand are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. There should be no space between the ligands and the metal within a coordination sphere. When the formula of a charged coordination entity is to be written without that of a counter ion, the charge is indicated outside the square brackets as right superscript with the number before the sign. For example, cobalt cyanide 3 minus, chromium water 3 plus, etc. The charge of cations is balanced by the charge of anions. Let's continue reading. For when the central metal atom is 1 in number, the formula of a compound is a shorthand tool. Let's continue reading that one itself. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination compound coordination entities contain a single central metal atoms. In other words, if a complex contains only single central metal atom, it is what we call a mononuclear coordination entity. The following rules are applied while writing the formulas. 1. The central atom is listed first. Second, ligands are listed in an alphabetical order. If it is an abbreviation, then the first letter of the abbreviation is considered in the alphabetical order, and this placement of ligand does not depend on its charge. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formulas are enclosed in parentheses, meaning brackets. Ligand abbreviations are also enclosed in parentheses. Even ligand abbreviations are enclosed in brackets, like for in case of EN, where the ethane 1,2 diamine, it was in such a way. Or for ligands like CN, like this is the parenthesis. There should be no space between the ligands and the metal within a coordination sphere. When the formula of a charged coordination entity is to be written without the counterion, the charge of the complex should be written as a right superscript with a number before the sign. For example, here we see that the -3, the 3 minus, it is written, and here the +3 charge in case of chromium and water. The charge of cation is balanced by the charge of anion. The next topic, naming of mononuclear coordination compounds. The names of the coordination compounds are derived by the following principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. Right. Let's read again. The name of the coordination compounds are derived by the following principle of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes in the name of the central atom along with any appropriate multipliers indicating the number of the ligands. Let's read a third time. The names of the coordination compounds are derived by the following principles of additive nomenclature. Thus, groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. The cation, first one, the cation is named first in both positively and negatively charged coordination entities. The ligands are named in an alphabetical order before the name of the central atom ion. This procedure is reversed from writing the formula. In writing the formula, we write like the metal ion first, then the ligand, but here it is reversed. Names of the anionic ligands end in -O or O. Those of neutral and cationic ligands are the same except aqua for water, amine for NH3, carbonyl for CO, and nitrosyl for NO. Ligands, prefixes based on alphabetical order. For anionic and neutral ligands, the ending should be with O, except for amine for NH2, aqua for water, carbonyl for CO, carbon monoxide, and nitrosyl for NO. While writing the formula of coordination entity, these are enclosed in brackets. Prefixes mono, tri, etc. are used to indicate the number of the individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the terms bis, tris, tetrakis are used. The ligand to which they refer being placed in the parenthesis. For example, NiCl2 PPH3 twice is named as dichlorido because it's a anionic ligand, because here the PPH group is twice, we name it as bis triphenyl phosphine nickel 2. Dichlorido bis triphenyl phosphine nickel. This is the name for NiCl2 PPH3 twice. Oxidation state of the metal in cation, anion, or neutral coordination entity is indicated by neutral Roman numeral in parenthesis. This is the one, the 2 numeral Roman number. If the complex ion is a cation, then the metal is named as the same element as the element. For example, cobalt in complex ion is called cobalt and platinum is called platinum. If the complex is an anion, the name of the metal ends with suffix -ate. Basically, in a complex, in a complex where the basic complex is CMI ligand, if this is positively charged, CMI will be CMI only or the metal name, but if it is negatively charged, then CMI element will end with the name of -ate. It is anionic if the complex is anionic. For example, cobalt in this one, it is negative complex, is called cobaltate. For some metals, the Latin names are used in the complex ion. Example, ferrate for iron, the neutral complex molecule is named similar to that of the complex ion, complex cation. The following example illustrates the nomenclature for coordination compounds. This complex with chromium as the central metal ion, with the complex is +3 charge, so we can call it as chromium, and based on NH3 we call it as amine, water we call it as aqua, and amine and aqua, M is first. As such, amine is the first, and since 3 amine is there, triamine, triaqua, chromium chloride. Here, since the complex is positively charged, it's a cation, that is why the name starts with the complex itself. But if it is a potassium, we write potassium here itself, where potassium is mostly always positive. Triamine, triaqua, chromium chloride. Explanation: the complex ion inside the square bracket, which is a cation, the amine ligands are named before the aqua ligands according to the alphabetical order. Since there are 3 chloride ions in the compound, the charge on the complex must be +3. Since the compound is electrically neutral, from the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecules, therefore the oxidation number of chromium must be the same as the charge of the complex ion. Here NH3 and water are neutral ligands. As such, chromium will have inside the complex a 0 charge, but the whole complex will have a charge of +3, so chromium will also have a charge of +3, or coordination number of oxidation state of +3. Next case, this compound is named as, here we see that this complex is as well as this complex is also a +6 charge, because SO4 has a -2 individual charge, and 3 molecules of SO4 will give it a -6 charge, whereas the complex charge will be +6. And here we see that cobalt is a central atom, and this one, ethane 1,2 diamine thrice is a ligand. As such, we can name it tris ethane 1,2 diamine cobalt 3 sulfate. How do we represent this? Cobalt is 3 is via this, because there are 2 complex here, there is a 2 here. Anyway, let's continue. The sulfate is the counter anion in this molecule. Since it takes 3 sulfate to bond with 2 complex ion, a charge on each complex cation must be +3. Further, ethane 1,2 diamine is a neutral molecule, so oxidation number of cobalt in the complex must be +3. Remember that you never have to indicate the number of cations and anions in the name of an ionic compound. The next is this compound, which is a double complex, which we can name it as AgNH3 twice and AgCN twice. Amine will have a special name of NH3 will have a special name of amine. We can call cyanide as cyanido. Amine should come first, so it will be diamine, silver 1, dicyanide, argentate. Here we have an example of here. Write the formulas of the following coordination compounds: tetraamine aqua chloride, tetraamine aqua chloride, cobalt 3 chloride. Since chloride is written at the last, the complex is a cation, a positive charge. It is a cobalt Cl H2O NH3 times 4. This is the answer. If we check here, it is indeed correct, except for the charge here, it is +2, or we can write as Cl2 minus 2. Let's go to the second compound. Potassium tetrahydroxozincate, where zinc is the main central metal atom, potassium is the counter ion. Tetrahydroxido zinc. Basically this must be the formula, but here they give K2. Yes, this is the, with potassium having a +2 charge, complex having a -2 charge, an anionic complex. And because it's an anionic complex, we wrote zinc as zincate. The third question, potassium trioxalato aluminate. Potassium trioxalato aluminium is the one. Oxalato is the C2O4 group. It is thrice. This is the formula. But here K3Al C2O4 thrice. Since the complex is -3 charge, potassium is +3, we call aluminium as aluminate. Thus fourth one, dichlorido base ethane 1,2 diamine cobalt. It's a neutral complex. Cobalt is the central metal atom. Cl2 En plus. This will be the formula. Next one, tetracarbonyl nickel. Tetracarbonyl nickel, also a neutral complex, NiCO4. Correct. In the next part of the question, write the IUPAC names of the following compounds. For the first compound, as a compound is a neutral one, you can call it as platinum. But before that, amine, chloride, and nitrosyl. Diamine, chlorido, nitrosyl, platinum. Diamine chlorido nitritol, it's not nitrosyl but nitrito, platinum 2, it is not 4 but 2. It is the first compound name. Let's try B. It's an anionic complex because we have potassium here. Tetrahydroxy zincato two, and first potassium wait, oops, I did the wrong one. The second one here, potassium is outside, so it's an anionic complex. Trioxalato chrominate, and potassium first, potassium trioxalato chrominate 6. Potassium trioxalato, not chrominate but chromate. It's not 6, it's 3. The next one, here it's a cationic complex. Base ethane 1,2 diamine, but I guess we should get chloride first. Dichlorido, bis ethane 1,2 diamine, cobalt 4 chloride, dichlorido, bis ethane 1,2 diamine, this is 3 chloride. Now next, this compound, here it is an cationic complex, so the name should be pentaamine carbonyl cobalt chloride. we need to call it carbonato cobalt 3 chloride, and the E compound, the last compound, where it's a anionic complex, mercury, that is the thiocyanato group, tetrakis, thiocyanato, cobalt, and the start being mercury. S cobalt 3. Okay, so I will continue the chapter, this chapter, tomorrow. Which we have have a good night.